Hi, let's take a look at one of the midterms, one of the versions of midterm 1 of Math 101 in 2024. It was February 9th of 2024. 3 questions, 45 minutes, no calculator, and the final answers should be only in calculator ready format. So let's begin by going to the first question together. In this problem, we are asked to take this integral. Let's begin by having a u substitution because we want to simplify what's under the square root so we have an easier integral. So let's call this u. So my u would be 1 plus x. From here I can conclude that du is equal to the derivative of this, which is just 1, and dx. And basically we don't need to substitute solve for dx because it's already solved here. And I just write it here, dx is equal to du. Now we can rewrite this integral. So this integral would be x minus 4 over square root of u times dx, which instead of dx we have du. Make sure that after any substitution, you don't see your previous variable. Everything should be in terms of a new variable. So everything should be in terms of u. So we need to somehow get rid of this x as well. So we want to write it in terms of u. So let's see what x is. So from here, I can rewrite that and say that u minus 1 equal to x. So from here, this integral would be u minus 1 for this x minus 4 over square root of u du. And about the bounds of this integral, we can keep it without any bounds and take the integral. And at the end, bring everything back, bring your variables back to x, or update the bounds. Just make sure that the bounds would not necessarily be 3 and 8 anymore. Let's update the bounds here as well. So these bounds 3 and 8 are for the variable x, but now we are changing the variable to u. So these bounds also should go through the substitution. So we simply plug 3 for this x in this substitution, and we get u is equal to 4. And this would be for the lower bound. And same for the upper bound. Upper bound here, 8 plus 1 is 8. 8 plus 1 is 9, sorry. So the upper bound would be 9. So these are the new bounds that we have. So we can just put it here as well. Or again, we can keep it as u and bring it at the end, the final answer, we bring it back in terms of x. Okay, so let's simplify it a little bit. So 4 to 9, u minus 1 minus 4, we have u minus 5. And instead of square root of u, let me just write it as u to the power of half u. From here, I can simply break down the fraction. So I can have this fraction as well as this fraction totally separated. So I can write this is equal to the integral from 4 to 9 u over u to the power of half minus 5 over u to the power of half u. And because I have two terms subtracted from each other or being added to each other, I can split the integral. So I can write 4 to 9 u over u to the power of half minus the integral, again I have du here, same bounds, 4 to 9, 5 over u to the power of half du. The main reason that I wrote that u to the power of half is here we can simplify it simply. The power of u up here is 1. So when we are dividing, we can subtract the powers. So what we get is the integral from 4 to 9, u to the power of 1, u to the power of half. When I subtract half from 1, I would get just half u minus the integral 4 to 9, 5 over this, or I can simply write 5 multiplied by u to the power of negative half, because negative power means reciprocal. It means it's in the denominator, eu. Now we can simply take the integral. The integral of u to the power of half is a power rule, which is u to the power of half plus 1, gives us 3 over 2 over this new power 3 over 2, and this integral would be the same still. There's a 5 which is a constant, so I just put minus 5 is a constant which is multiplied, it stays there, and u to the power of negative half would be u to the power of negative half plus 1, basically it's positive half, over this new power half. And again, this is, I took the integral, I will plug in the bounds here, which are 4 and 9. Let's just make it, rearrange it in a better way. So instead of dividing by 3 over 2, I can multiply by reciprocal of that. So I can write u to the power of 3 over 2 multiplied by reciprocal of 3 over 2, which is 2 over 3, minus 5 times u to the power of half divided by these, or basically multiplied by the reciprocal multiplied by 2. So this is what we get from 4 to 9. Now I can simply plug in 9 here. So it would be 9 to the power of 3 over 2 times 2 over 3 minus 5 times 9 to the power of 3 over 2 times 2. This is what I have for the upper bound. Let me use to the left. And minus when I plug in the lower bound. Okay. It would be 4 to the power of 3 over 2 times 2 over 3 minus 5 times 4 to the power of 3 over 2, sorry, 1 over 2. Made a mistake here as well. Times 2. But what is 9 to the power of 3 over 2 or 9 to the power of half? Power half in both of them means square root. So instead of 9 to the power of 3 over 2, we can have square root of 9 to the power of 3. Or here we can have square root of just 9. So denominator of the power is basically the roots of that. And the power, the numerator is just normal power. The same goes with these 4 and this one. So what we will have is square root of 9 is 3. 3 to the power of 3 is 27. So we have 27 times 2 over 3 minus 5 times square root of 9 again is 3 times 3 times 2 for the upper bound minus the lower bound, which is 4 to the power of 3 over 2. So it's square root of 4 to the power of 3. The square root of 4 is 2. 2 to the power of 3 is 8. So we have 8 times 2 over 3 minus 5 times square root of 4, which is 2 times 2. Let's see if we can simplify anything here. So I can reduce this 3 and 27. It becomes 9. And 9 times 2 is 18 minus 5 times 3 times 2, which is 30. What I get when I plug in the upper bound minus when I plug in the lower bound. 8 times 2 over 3. Okay, I cannot simplify these two. So I just have 8 times 2 is 16. So 16 over 3 minus this product, which is 20. So I can write it this way. 18 minus 30. I distribute this negative, so it's minus 16 over 3 and plus 20. Which overall gives us, okay, 18 plus 20 is 38, minus 30, it is 8. It's 8 minus 16 over 3. And the common denominator 3, I can write that as 24 over 3, and this stays as 16. And we are subtracting. Subtracting 16 from 23 gives us 8, and the denominator 3. So this would be the final answer. So we did that by applying the u substitution for what we have under the square root, and then splitting this fraction into two parts with the same denominator, and after that just simple power rule. In this problem, we are asked to take this integral, which is an indefinite integral. We don't have any bounds. So if we do any substitution, we need to bring everything back in terms of x. One thing here that we see is we have this x in the denominator, or basically we have 1 over x, and also log. This combination is a very common combination, and it's perfect for u substitution. And the main reason is 1 over x is the derivative of log. So what I would do, I would start with writing u is equal to log of 5x, and make sure that I don't include the power 2, because the power 2, when I take the du, it will overcomplicate the derivative, which it's more complex than just 1 over x. So I totally exclude that. So it's just log of 5x. Let's evaluate the du and see if it's helpful or not. The derivative of log is 1 over whatever is inside of that, multiplied by the derivative of inside because of a chain rule, multiplied by 5. Here we see that we can simply cancel these two 5s, and we get 1 over x. At the end, we have dx. The dx here as well. So from here, let me just rewrite that. Du is equal to 1 over x dx. A tiny substitute, kind of rearrangement, we can write dx is equal to x du, just multiplying both sides by x. So we have x, dx is equal to x du. Now we can rewrite this integral. So the integral on top, we have just 1 x. This bracket, we have 1 minus log of 5x entirely squared, or basically just u squared, and that part is raised to the power of 3 over 2, multiplied by dx, and instead of dx I can write x du. This is a good substitution because it helps me to get rid of these x as well, and I have a little bit simpler integral. So now we have integral of basically du over 1 minus u squared to the power of 3 over 2. So now at this point, I mean, right now I don't know what is the derivative integral of that. So or I don't know this is the derivative of what function. So we need to apply other methods that we know for integrals. What we see here is 1 minus u squared. And if you recall, when we have 1 minus x squared, 1 plus x squared, or x squared minus 1, these are perfect trig substitution templates. Not necessarily 1, just any positive number, basically. We have 1 minus u squared, which is basically one of these templates. And if you recall trig substitution, for this one, u equal to sine of theta is the best substitution. And you will see why, because after this substitution, this summation converts to a multiplication. So this negative sign will kind of become multiplication between two other terms. And the main point of that is we can easily raise it to the power of 3 over 2. So what we can do here is, this is u. Let's evaluate the du, which is the derivative of this part. It is cosine of theta multiplied by d of that, d theta. And here, do not evaluate d theta because we don't need it. We want du, so we kind of stop here. So it's a little bit different from u substitution. So we want du, we have it here. Perfect. So now I can rewrite the integral. Instead of du, I have cosine of theta, d theta on top, and the denominator would be 1 minus u squared, or in this case, I mean, after the substitution, minus square of theta, and all of that to the power of 3 over 2. What's the point of doing this? Again, we need to focus on this part, and we need to apply some of the identities, trig identities that we know already. So 1 minus sine squared of theta. So the idea that we are going to use is 1 minus sine squared of theta is equal to cosine squared of theta. So I can rewrite this integral as integral of cosine of theta d theta over the entire bracket would be cosine squared of theta, which is raised to the power of 3 over 2. So we have basically cos of theta to the power of 2, then to the power of 3 over 2. And now when we have multiple powers like these, kind of in different brackets, something like x to the power of a to the power of b, or maybe then to the power of c, these powers get multiplied by each other. So these 2 and these 3 over 2 get multiplied by each other. And make sure that here I couldn't do that because of these minus. I cannot just simply distribute these 3 over 2 to these parts. And the main purpose of doing the trig substitution was getting rid of this minus, using some of the identities that we already know, and make it just one term or multiple terms that are multiplied by each other. If you have two terms that are multiplied by each other and raise them to the power of something, you can distribute this power. But if there is a plus or minus sign, you cannot do that. So here we simply write that as cosine of theta d theta on top, and the denominator would be 2 times 3 over 2 as the power of cosine, which 2 times 3 over 2 is simply just 3. And now we can kind of simplify even further, because we have 1 cosine of theta on top and we have 3 cosine of theta in the denominator. So we can divide them, we can cancel them. So on top there is nothing left, but the denominator we have cosine squared of theta. So now we have a way simpler integral, which we can kind of focus on this one. Which this one is basically 1 over cosine squared of theta. If you think about some of the other trig values, trig functions that we already know, one of them is secant of theta. Secant of theta is 1 over cosine of theta. What we have here is, let me just rewrite that, it is 1 over cosine squared of theta d theta. So what we have here is a squared of that. So basically we have secant squared of theta, which is 1 over cosine squared of theta. So instead of the 1 over cosine squared of theta, I can simply write secant squared of theta. How does it help? It helps us in a way that we already know a function, or we should know the function, that its derivative is secant squared of theta. And that function is tangent. The derivative of tangent is secant squared. So if I reverse this derivative process, the integral of secant squared would be tangent of theta. This is a indefinite integral, so there is a plus c at the end. So this is the final answer to this part. But again, because this is an indefinite integral originally, we need to bring everything back in terms of x. So let's see what theta is. The theta was first introduced here. U is equal to sine of theta. Let's see what is theta. So from here, if I take the arc sine of both sides, what do I get? Arc sine of u is equal to arc sine of theta. And why I'm doing this? Because here arc sine and sine cancel each other, so I have theta is equal to arc sine of u. So now basically let me just write it right here. So from here theta is equal to arc sine. So instead of this theta, I can write arc sine of u. So this is equal to tan of arc sine of u plus c. And then we can go back and see what u is. U is introduce here. U is log of 5x. Then we can put it here and get the final answer. But before getting that final answer, let me spend kind of maybe 1 or 2 minutes to simplify this part. Simplify tan of arc sine of u. So let's do it in page. Tan of arc sine of u. Just focusing on this part. And again, if you plug in, instead of u, if you plug in log of 5x, what we have here, this is correct. This is kind of final answer. But if you want to have a more simplified version of that answer, we need to focus on this part and simplify this. Tan of arc sine of u. So what I can do, I can say arc sine of u is theta. This is basically what we had, because the nature of arc sine or arc cosine or arc tan, all of them are angles. So I can say theta is equal to arc sine of u. So from here, I can say that sine of theta is equal to u. This is kind of something that we had. But the reason that I'm doing this, I can relate that to a triangle here. So I design one triangle that it has an angle theta, and sine of that is u. So what is sine? Sine is opposite over hypotenuse. So the opposite of this, theta, basically this, over this side should be equal to u. So I can say, let's call this one u and this one 1. So if the length of this is u, the length of the hypotenuse is 1, u over 1 would be sine of theta. So what? So here, what we want to evaluate is tan of arc sine of u, or basically tan of theta. Because we said, let's call these theta. So what's tan of theta? Again, we stick to this triangle. What is tan of theta? Tan of theta is opposite over adjacent, basically opposite u over adjacent. Let's evaluate the length of these. How do we do that? We do that by using Pythagoras. So this side is square root of 1 minus u squared. If you don't remember Pythagoras, for a right angle triangle, if you have a, b, c as the sides, a squared plus b squared equal to c squared. So we are basically using Pythagoras here. So we can say, okay, the adjacent is square root of 1 minus u squared, which is square u squared. So this tan of arc sine of u plus c can be replaced by this. So we can replace that by saying that that integral, the initial integral, I just write integral here, is equal to u over square root of 1 minus u squared plus c. And again, what is u? We know that we introduce u as log of 5x. So the integral is equal to log of 5x over square root of 1 minus log of 5x squared plus c. So this would be basically the final answer to this question. Again, and also consider that log and ln, they are same. So if you use any of them, that also works. In this question, two runners, A and B, are running 300-meter race on a straight race track, and we know the velocity of a runner A, and also we know that the runner B is running in a way that they have a constant acceleration, and they caught up with runner A after 5 seconds. So let's kind of translate this in more mathematical terms so it's easier to understand. Let's begin with quickly visualize this on a graph. So two runners, both of them are starting at rest at the velocity 0, I'm drawing their velocity with respect to time. At time 0, their velocity is 0, both of them. And right now I'm just drawing the velocity as a sketch for runner A. So first, for the first 3 seconds, 0 to 3, it has this function, 3t squared. So it's a parabola like this. And after that, after 3 seconds, the speed is constant 27. The velocity is constant 27, which it would be something like that. And the reason that I know they are connected to each other is if I plug in 3 into this function, I get 27, which is same as this number, which is basically they are continuous. They are kind of connected and the function is continuous. But this is the velocity function for runner A. But how about runner B? Runner B has a constant acceleration. So starting at the point here, starting point, to the very end point of 300 meter, they have a constant acceleration, which means the rate of change of velocity, which is called acceleration, is constant. Or it means basically it has a straight line with a positive slope. And why positive slope? Because they are accelerating. So they have some function like this. What we know about B is, the runner B is, they caught up with runner A in 5 seconds. So at the moment 5 seconds, they are at the same place. Please make sure that caught up doesn't mean that they have the same velocity. They are at the same point. So basically it doesn't mean that, for example, this is a cutoff point or this one, because at those points the velocities are same. What we want is their position to be same. So what we know is displacement is integral of velocity. So integral of velocity is displacement. Basically, the area under these curves is the displacement of each runner. And when they say the runner B caught up with runner A in 5 seconds, it means after 5 seconds, I don't know where it is. Let's say it's here, 5 seconds. It means the area under the green curve, or basically the integral of that, is equal to area under the red curve. Basically their displacement or their distance from the initial point, the start point, is same, so they are at the same place. That's the idea behind this question. The integrals are same. So for runner B, I know it's a straight line like this. It's a straight acceleration. So I can say the velocity of a runner B is a function like a times t, which a is a positive number. It really doesn't matter if I just write that, but positive number because it's acceleration. If it was a deceleration, it would be minus. And there is no plus b anything here, and the reason is it starts at 0, so basically the y intercept is 0. So from the fact that it's a constant acceleration, we know this is the velocity of the runner B. And because after 5 seconds they are at the same place, their integrals are same. So let's take that. The integral from 0 to 5 of the velocity of the runner A, dt, with respect to time, is same as integral from 0 to 5 of velocity of the runner B, dt. For runner A, we know the function. We know it's a piecewise function, and it's made of 2 pieces. 0 to 3 has a different function, has a different expression, and after 3 is a different expression. So we need to break down this integral for runner A. For runner A, I write it as 0 to 3. Velocity of the runner A, I will replace it later. And from 3 to the last endpoint 5, velocity A, E, it's equal to integral 0 to 5 of runner B velocity, which is a, just a times t. And a is just a random arbitrary parameter, just it's a constant positive number, dt. VA from 0 to 3 has this expression, 3t squared. So I can replace this VA with 3t squared. This VA, 3 to 5. 3 to 5 means basically after 3, which is just constant 27. So instead of the VA at this, in this integral, I can write 7. So what I get is this integral. So let's just take that. So the 3 is a constant, stays there. T squared is t to the power of 3. I add 1 to the power over the new power. And the bounds for this is 0 to 3 plus this integral, 27, and just t, because the derivative of 27t is just 27. And the bounds are 3 and 5. And the last part is this. A is a constant, it stays there. And the power of this t is 1. So it would be t to the power of 1 plus 1 or 2 over 2. And the bounds here are 0 to 5. Let's evaluate each of them. So first we plug in the upper bound here. Or before that, let me just cancel these 3 with these 3. First, I plug in the upper bound to this. I get 3 cubed minus when I plug in the lower bound, which is 0 cubed. So this is the first integral plus the second integral. I have 27 times when I plug in the upper bound, 5, minus 27 times when I plug in the lower bound, 3. And it is equal to a times when I plug in 5 squared over 2 minus when I plug in 0, a times 0 squared over 2. This part is 0, this part is 0, so we don't need to care about them. So what we get here is 27 plus this part, which is 27 times 5. I just write it for now as this, minus 27 times 3. And it is equal to 5 squared, which is 25. A times 25 over 2. Here, to do it simpler, I factor out 27. So I get 1, 5 minus 3. And the right hand side is a times 25 over 2. 1 plus 5, 6. 6 minus 3 is 3. So I have 27 times 3 equal to a times 25 over 2. And 27 times 3 is just 81. Now I can simply isolate for a. So a, okay, what I do is I multiply both sides by the reciprocal of these, 2 over 5. It helps me to get rid of these parts. So a is equal to 81 times 2 is 162 over 25. That is a. So now I know the velocity of a runner B is 162 over 25 t, because we said that's a linear function, because it's a constant acceleration, and that is at. So basically this is the velocity of runner B. But we didn't want this. What we wanted is how long it takes for runner B to finish the race. The entire race is 300 meters. So basically, to finish this race, each runner should displace 300 meters. So the integral of the velocity of the runner B or runner A, any of them which wants to finish, both of them basically, but we care for runner B at this point, from 0 to the final time, let me just write it t, the t of the time, finish time, yeah, finish time, should be equal to 300. This is the race length. So now the question is what this t is. So let's take this integral. We already have that integral. Let me just do it again. 0 to t 162 over 20 dt is equal to integral from sorry, let's just take the integral 162 over 25. It stays there, and t would be just t squared, and the bounds are 0, and so it would be 162 t squared over 25 and 2 multiplied to 50 minus, when I plug in 0, which is just 0, so I don't need to write that part. So this is the displacement of runner B after this many seconds, basically. And we want to figure out when this would be 300. 162 t squared over 50 is equal to 300. So let's change rearrangements. So t squared is equal to 300. What I'm gonna do is multiply both sides by 50 over 162. So there's a 51 over 62 here, and the left hand side, these parts get cancelled. Let's see if we can simplify some of these terms. 162 and 300 cancels to 54 here, and cancel these 50 and these 54 becomes 25, this becomes 7. So we have t squared is equal to 25 times 100 over 27. Get a little bit down. So what is the time? Time is the square root of that. Square root of 25 times 100 over 27, which a square root of 25 is 5, the square root of 100 is 10, square root of 27 is, we can just leave it as is, or we can write it as 3 square root of 3, which is kind of the same thing, doesn't really matter. So the time would be 50 over square root of 7. And the reason that I could distribute the square root is everything here is multiplication or the division. So if I had a plus sign, I couldn't do that. So at the final point, kind of this would be the overall time, how long it takes for runner B to finish the race.